elsewhere. So we're in luck. We get to have school today. ECU's canceled, and Southwestern lost all electricity. They're canceled. So
how did they lose all their electricity?
big ice storm out there. I guess taking a power grid coming into town. So the town's black. Anyway, so it's going to go over this. So just looking at the definitions. First of all, the hard copy of the keys posted on the cork board down by 214. So if you want to look at any of the answers in detail and not review this video, you can look at those.
We need to keep this right.
Say
We
again?
need to keep this right.
Yeah, absolutely. So the definitions, I'm looking for some key words. It doesn't have to match my wording. But sensitivity, what I'm looking for is the ability to distinguish between two concentrations. That's one way we think about it. If you would have simply told me the slope of the calibration curve, I accepted that as well. Okay, so, but that's what when you look at the slope of the calibration curve, that's what your information you're getting out of it. Selectivity is the ability to see the analyte and separate or resolve its signal from anything else in the sample matrix. Root mean square current is a current of an AC that produces the same power as an equivalent DC circuit. Flicker noise is a noise characterized being proportional to 1 over the frequency of the signal observed, and it becomes an issue with low frequency signals, something less than 100 hertz, and long-term drift, just as we usually think about it. And thinking about what is a photon, the particle model, it represents individual bundles or packets of energy. We also call it the quanti. It's the smallest unit of energy, the smallest discrete unit of electromagnetic radiation that can exist. So I'm looking at how close you got. We actually did very good as a class on our electronics question. So I gave you this circuit, had some things in series and 2 resistors in parallel. First thing I wanted to know was what was the voltage drop across the points C to D, which is the 900 ohm resistor. So to do that, you need to know the total resistance in the current or the circuit. So you need to know what was R parallel. So R parallel was the inverse of 220 plus the inverse of 500. Take the inverse of that, R parallel was 153 ohms. So then you just set it up as a voltage divider. You had a 20 volt source. 900 ohms were dropped across the element of interest. You add all the other components together and you get 10 volts if you went to 3 sig figs. And then the next one, I asked what is the current flow across the 200 ohm resistor. So if I just look, or the 220 ohm resistor, what is the current flow that's going across this guy? Okay, so if I consider this, what I need to do first is find out what is the total current in the system. So the total current is going to be the voltage divided by the total resistance. So it's the 20 volts. Again, we've already found the resistance parallel, so 900 plus 153 plus 750. And I may have plugged a number in the calculator wrong. I got 11.4. I think everybody else did 11.1. So I think I probably made the math error since y'all were common at 11.1. And then if we take it and set up the voltage divider or current divider equation, so we take the current, and then it's the current as it flows, all of the currents going across the first resistor. So if you think the current's going through here, I total is going across the 750. I total is also going across the 900. But when the current gets to the systems in parallel, it's going to divide across the 2 resistors. And it's going to choose the path of least resistance. So I know the total resistance in this series in parallel, or this circuits in parallel, is 153 ohms. Oh, I see my mistake. It was 220, and I put 200 in here. That's the reason my number was slightly off. So when you did this, you should have got 7.7. That was my math error that I got. So the 153 divided by 220 ohms times the total current flow, you got 0.077 or 7.7 milliamps if you look at the milliamps of circuit. But we did really good on those as a class. All right. So looking at the multiple choice, we're a little mixed on the multiple choice on the next page. I'm going to go over these very quickly. So the first one says the noise is likely to be reduced by a high-pass RC filter. So we could get the noise that's high-pass. We're going to transmit high-frequency signals, and we're going to reduce or eliminate, block, if you want to think of it, low-frequency noise, and that's associated with flicker noise. All right, when electromagnetic radiation goes through matter with a high refractive index, I ask you some different things. So the velocity slows down, so it's not A. The frequency increases, the frequency decreases, or B and D. No, the frequency stays the same. What changes is the wavelength compresses, it gets shorter. Which of the following does a transformer do? A transformer increases or decreases the line voltage from an AC source. Which type of electromagnetic radiation is associated with the excitation of core electrons from atoms? That was on that table. I told you you're going to have a question over that. It's X-rays or core. UV or valence electrons, but core electrons are X-rays. And which device has a nonlinear electrical device has a greater conduction in the forward direction than the reverse? That's a diode. I think we all did well on that one. Okay. And then we got tripped up a little bit. So I gave you number 8. So I tell you that you've got a 5 ml sample has paraxylene. It's analyzed using gas chromatography, and it gave you a certain signal. All right, and I tell you, this is your unknown. You took another 50 mils of that sample, and you spiked it. You added exactly 5 mils of a known concentration of standard of the same stuff to it, and you reanalyzed it, and it gave you this new signal. So I want to know what's the concentration in the original sample. So you analyzed the sample, then you spiked it, you add a known amount to it. That's standard addition calibration. All right, and Casey, you tried to work it as the question with F. That was the method of internal standards where you did the F ratio, but the fact that you said it was 1 actually turns out to exactly the same thing. So if you took the two equations and put them equal to each other, if S is equal to 1, they drop out, become the same thing. But what you simply do is set up the ratio of the concentrations is equal to the ratio of the signals. So the original sample produced this signal. The second sample that spiked produced this signal. And then you had to find out what's the concentration. So I took 5 mils of this known concentration, and it was in a 55 mil volume. I started with 50, I added 5 to it, so now it's in 55. The original sample, I had 50 mils of it, but now it's in 55, so it's diluted by that 10 to 11 ratio, or 5 divided by 55. For that point, it's just a math problem because only variable I have here is X. So all I did was take and multiplied this out, got a number, divided this out, got a number.
Why on the second one, 50 over 55?
Okay, and divided the thing on the right over the number. Say again,
Why
Casey?
is the second one 50 over 55?
Okay, I started with a 50 mil sample, and I added 5 mils to it. So the total volume is now 55.
I thought I just wanted to know the original sample. It's just a second aliquot.
Well, it is the original sample, but when we're comparing this signal, we're having to look at what's the effect of the concentration. You've diluted it some. So that's what we have to do is account for the dilution that occurs. All right? So when you do the math solve X, you get X is 5.16 times 10 to the minus 6 molar paraxylene. So it's just an algebra problem at that point. Okay. There were other ones, certainly, than these that I gave you credit for. So when you're choosing a method, what are the factors that must be considered? I just asked you to name 4 of them. Accuracy, how much samples available, concentration range of the analyte, the sample matrix, how many samples to be analyzed, what is the analyte, accepted operator training, available equipment. I mean, there was a bunch of them. As long as it was one of the ones that a couple of you put things like equipment that's available and which methods are available, those are the same thing. So I didn't give you credit for both of those, but as long as it was one of these other things that we have to consider, you got credit on that one. Okay, we struggled on this one a little bit, so I told you to know the graphs. This was one of them that we talked about a little bit. So if you, I wanted to know the output from a diode in terms of an ohm, it's called an Ohm's law plot. It's a plot of current versus voltage. And in the forward direction, okay, when it's set up and it's drawn in the forward direction, it obeys Ohm's law. So it's a linear plot of current versus voltage. But in the reverse direction, what happens is there's no current flow in the reverse direction, so the current flows at 0 until you hit what's called the breakdown voltage, and then current starts to flow freely. That's the reason we use these to control voltage in systems, something called a Zener diode. It's just a variation of this. But whenever you see one of these circuits, these devices in a circuit, a diode is going to be set up something like this. So there's a positive side and a negative side to the circuit, and it just depends on which way the potential is hooked up. Is it hooked up in the positive, so you have the positive terminal of the source coming in, so this would be reverse bias mode. If it was switched around, it'd be positive bias mode. Okay, this one should have been predictable, and I think we did well on it. So you've got a data set. Calculate the signal-to-noise ratio. Signal-to-noise ratio is equal to the average divided by the standard deviation. So the average of that set was 2.15 with an insignificant 7. The standard deviation was 0.125, comes up to a signal noise of 10.0. B was, now that you've got that data set, calculate the how many scans must be obtained, or replicates, to get a signal noise of 25. We know that signal to noise is proportional to the square root of the number of scans. So you set the ratio up of 10 scans to the square root of 7, or signal noise of 10 to the square root of 7, number of scans, to 25 to the square root of the number of scans that I want to go with that. When you solve for the number of scans, it's 4375, and you always have to round up to make it a whole number. It takes 44 scans, and I think we all got that. Okay, so this one was one we had issues with to some degree. So I tell you, you have a lead analysis. You did flame emission spectroscopy, and you got this calibration curve out of it. And I had to correct my my y-intercept. I didn't get my zeros in there when I wrote it out. So signal is equal to the slope of the calibration curve times the concentration in parts per million. And I tell you that you took the blank, and the mean value for the blank is this, and it had a standard deviation associated with this term for 20 measurements. So I wanted you to calculate the limit of detection for the method. So there was an equation on the equation sheet that says the signal at the limit of detection is equal to the signal of the blank plus 3 times the standard deviation of the blank. So we have the signal for the blank, this term, plus 3 times the standard deviation for the blank. Okay, so that was this term. That tells me my signal at the limit of detection is this 0.0585. So what I need to do then is take that number and plug it into the calibration curve up here. So now I've got my signal, And what I simply do is find out what is the concentration that's responsible for that signal. So when you do that, solve for C, and the units of it are parts per million. I tell you the units, you get 0.031 parts per million. That's 31 parts per billion. That's a pretty decent sensitivity. But lead's one of the things we're concerned about. 31 parts per billion is above the allowable limit for something for human consumption. So we had a problem that we'll talk about as the semester goes on with orange juice. I may have already mentioned it. If you grow like oranges that were grown in Tijuana, Mexico, right next to the California border, those oranges, the water in Tijuana is highly polluted. And citrate compounds leach metals very well out of the soil. So for 40 years, the state of Mexico, or the state of California, was buying the cheaper oranges from Mexico, shipping them up, making orange juice, giving to the school kids. And then they started, well, let's look at that orange juice for the heck of it, start testing it, and realized that it was averaging 50 parts per billion lead. Because they were watering the oranges with the industrial waste from the plants down there that was contaminated with lead. So that's the reason people in California act like they do, I guess. I don't know. But the sad thing is that there was a lot of juice that was contaminated for a long period of time, and I'm sure those were the worst case batches. Today, everything that's given to children in California has to be tested, and for the most part, they won't allow the import of fruits anymore for human consumption in school programs. European Union even has stricter standards. European Union tests absolutely every sample that's come out in human consumption. So the EU is, it's hard for a lot of companies in the United States to even deal with Europe because of this restriction, because they have a higher standard for public health than we have in the United States. All right, limit of quantification, LOQ. It's this average signal of the blank plus 10 times the standard deviation of the blank. So that gives you the signal of 0.1082. You do the same thing, plug it in the equation, and you find that your concentration now for quantification is around 60 parts per billion, 59. So we can see it at 31 parts per billion, but to quantitatively say, I can say there's something there at 31. To be able to say how much is there, it's got to be 59 parts per billion or higher. That's the information we're getting out of that. All right, 13, what does the Nyquist sampling theorem tell us about the sampling rate when we're digitizing a signal? That the sampling rate should be 2 times higher than the highest frequency component in that signal. So if I've got a signal that has a 60, 120, and a 400 hertz signal, if I want to describe those combinations, so if those frequencies are combined, what type of pattern? If I have an AC signal that has different frequencies in it, what type of pattern is that going to produce? It's going to be a beat. Okay, so it's going to be a wave packet, increasing, decreasing, increasing, decreasing. So if I'm going to sample that and define it like I would have to in NMR and IR, if the 400 frequency hertz is the highest frequency, I need to sample it at least 800 hertz to be able to correctly define that signal. All right, what is boxcar averaging, and when is the appropriate time to apply it? Boxcar takes a number of points and averages them together with the assumption that the average is better than, of a group of points is better than any one data point. And I tried to do my graphs didn't look too great, but you take a number of points, average them together, get a representative points, another number of points, average them together, get representative points. You can change the size of the box card depending on how quick your data set is changing, how noisy it is. When it works well is when you have a slowly changing signal, because you lose some signal detail with this. And then finally, I gave you a bonus question. We didn't really work an example like it, but we talked about Schnell's law, which is the equation used to solve this. So I tell you that the D line of sodium strikes an air diamond interface with a certain angle. The incident angle is 25 degrees. So it's coming in at 25 degrees in air. And I tell you the refracted angle is measured at 10.1 degrees inside of the diamond. And I want to know what's the refractive index for the diamond, considering the refractive index of the air is approximately 1. So you simply set up Snell's law. It says the ratio of the angles is equal to the inverse of the ratio of the refractive indexes. So when I say the inverse, this one's paired up with this one. This guy's paired up with this one. So I just plug the numbers in, find out what end of the diamond is, and refractive index for diamonds is about 2. Okay? So overall on the test, the average was okay. I mean, certainly I'm not going to gripe about an average of, we were in the 70s. So the average was 78. We didn't quite have the range we'd like to have, but everybody passed the test, so I'm not going to gripe too much on it. So, say again?
Casey's holding that average up.
Yeah, Casey is supporting the class.
Can I see the answer number 8 real quick? Again?
Yeah, let's go back. Okay. Okay, this is the standards edition. Okay. And I didn't bring the equation sheet, but it basically, if you look at the equation sheet, it was, well, the formula that's on the top left there. It's the ratio of the concentrations divided by the ratio of the signals. The key thing to do this one is realizing that whatever you spike it with, you have to dilute it down a certain ratio. And when you do that on the bottom, your sample's diluted at the same time. Okay.
So could you just you do the 5 milliliters times the concentration, get the molar amount, and then just divide that by new total volume to be like the concentration?
Yeah, that's exactly what I did right here.
Okay.
Yeah. So absolutely. So and as soon as you get the equations, I'll write it all out in one step so I can make sure that I can see. I've got to account for the total volume, but if I can see the 5s here and 55s here, those two things add together, or the 5 and the 50, those add to the 55. That's just my mental check of that I've got everything represented. But as soon as you can get it into a numerical form, lots better. So, okay. All right. The thing I'll tell you about the next test, this one we were kind of talked about some wildly different topics. The next test we're going to be a lot more focused. Okay, so we're going to start diving into some techniques. We're going to finish up chapter 6, and we'll roll right into chapter 7. Start looking at visible or optical spectroscopy, and from that, I mean, we're really going to pick on some more exact things than I'd say just going all over the place. Okay, so I've got to leave. I've got to get my son to an ortho appointment. So I've got to leave about 10 minutes early. So if I don't stop you if I don't stop at 9:40, that's my intention. So we're going to get about 15 minutes worth of stuff in here to work towards finishing up chapter 6. Chapter 7 notes have already been posted. I don't think we'll get there today by any means, but we're going to roll right into chapter 7 following this up. So the last thing we talked about is how spectra could be very different depending on what the nature of the analyte is, and then even the phase of the sample. So going from a vapor, so something that's in a gas phase, is an example of the benzene's vapor. So this is something that's in a gas phase, versus here it's in a liquid. It's in hexane, but if I would take benzene and run it in a different solvent, even the change in solvent, delta solvent, will cause the spectra to shift. In fact, we'll learn when we do UV spectroscopy, I can tell if something will hydrogen bond or not by knowing which way it shifts if I go to a more polar solvent. So we can actually learn something about our compounds by looking at changes in the solvents and how spectra shift. And even we said with the overall structure, if you go from something like an aromatic, single aromatic, a benzene, to something that's a bridged aromatic biphenyl, it has an enormous change in the spectra. Okay, so now we're going to start focusing on atomic species. So atomic, when we talk about atomic techniques, whether it's atomic emission, atomic absorption, anything when we say the word atomic, we're talking about discrete atoms. And it doesn't matter what form of sample we feed into the instrument necessarily. It can be a molecular compound, provided that there's some type of a treatment inside of the instrument that will degradate chemical bonds and present the sample in the form of discrete atoms when it's going to interact with the electromagnetic radiation. And a way that we'll do this experiment this semester is an atomic absorption spectroscopy. You can put in a molecular form of a metal, but we're going to expose it to a flame at 3,500 degrees, and that very high temperature is going to break chemical bonds. It's going to get it down to the discrete metal atom. Another way that we do it is we inject a sample in a plasma that's at 10,000 Kelvin. And a similar type of thing is going to occur. It's going to break down any chemical bonds, and it's going to get us down to discrete atoms in the system. Right, so whenever we put UV vis light through an atomic substance, so something's got these discrete atoms in it, we can have an absorption, which is an excitation event that occurs by the electronic process in which valence electrons are promoted to a higher energy level. And this is what we talked about as E-electronic. So it's not the core electrons, it's the valence electrons. Remember I told you there are, if I talk about the total energy that can exist, it was E-electronic plus E-rotational plus E-vibrational. But there's only a limited number of transitions that can occur with atoms because they don't have bonds. And if they don't have bonds, there's only a single thing. They can't vibrate or they can't rotate. That means that there's only a limited number of transitions that can occur. So spectra are typically relatively simple with atomic species compared to molecular species. And because of that, we call these line spectra because we'll see that the lines are very, very sharp. I'm going to cheat ahead here. So this figure doesn't do it justice. Okay, so I've jumped forward into chapter 7's notes. Let's see. I think I unloaded that far. I'm not going to jump forward in chapter 7's notes. Let's look at energy. Okay, so this is modeling. We don't want modeling. I want something real. Okay, this is a representative spectra of. This is actually studying light from this is solar radiation, so coming from the sun. But these are examples of the different atoms that are emitting off different components. And these are primarily iron. They're all emission things coming from iron. And they're varying a little bit about what the oxidation state of the iron is and what the charge is. But remember, we said an angstrom was a tenth of an nanometer. So this is an angstrom scale. Okay, so these are way down in the UV when we're looking at these. So this is stuff that's being done in outer space. But these line widths in terms of nanometers, if this is this would be going from that one point to the other. Didn't mean to launch that. We're going from this to this, even though that's 5 angstroms, that's 0.5 nanometers. So these line widths for these spectras are literally hundredths of a nanometer wide. Okay, they're super narrow, and that's the point I really want to illustrate. That, I mean, we're not doing it justice when we say that they're as broad as this picture represents. They are, with atomic species, are very, very narrow associated. So what happens when you have an absorption? An absorption occurs as quick as a wave can go up and down. So if we think of the electromagnetic radiation model, and as quick as a wave can go up and down, and we know that in the UV vis, this occurs in 10 to the frequency is about 10 to the 15 hertz. So it's going up and down in a 10 to the 15th of a second, or a femtosecond. As quick as a wave can go up and down, a photon is captured or absorbed, a quantity of energy. That's the oscillation of a wave. So it gets promoted from a lower energy level to a higher level. And then once it gets excited, it stays in the excited state for atomic species, typically only nanoseconds, but that's still a long time compared to how quick it absorbs. Nano is 10 to the minus 9th, where this guy is a femtosecond. The 10 to the minus 15th is a femtosecond, FS, femtosecond. Okay, and then once it's been excited, it wants to lose this energy off, and the mechanism it loses energy off can vary a little bit. It can occur by a collision, but that's going to depend on the density of the gas or the substance that it is, that it's in. How soon is it going to be before it runs into anything? How high is the kinetic energy? Or it can occur by the emission of light giving a photon off. Now, what transitions are going to occur are described by something called the selection rules. And they predict the transitions based on quantum mechanics, way beyond the scope of this course. But if we look at something like the valence electrons, that's what's happening in the UV vis. And this is for sodium, so this is a signal for sodium. And if I look at sodium's electron configuration, okay, go back in time. Tell me, how many electrons does sodium have? Neutral sodium. Okay, it's got 11 electrons. Let's write out its electron configuration. 1s2, 2s2, 2p6. Okay, that's used 10 electrons. I got 1 left, 3s1. Okay, the only valence electron here is the one in the outermost shell. So there's only one valence electron that exists in sodium, neutral sodium atom. So if I take a sodium, if I light a match, I look at the colors, the main color I see is this orange color at 590, and it's actually two different lines there. It's a 598.6 and a 590, but that takes really high resolution to pull those two apart. And if I went and studied down in the UV, there's two other transitions that occur in the UV. So what these transitions occur are the 3s electron being promoted to different levels. The strongest emission that we see, the one that's at the highest wavelength or the lowest energy, is the jump from the 3s to the 3p. That's the absorption. And if I'm looking at the light coming off, it would be the emission. It would be that falling back down. Okay, so that's the 590 nanometers associated with that. And then there's these bigger energy jumps that occur from the 4s to the 5p or 4p and then the 5p. But the one that's missing in here is what happened to the 4s transition. And it's not an allowed transition. That's what it comes down to. So this is a crude table, but This shows the energies associated with some of the allowed transitions that are dictated or predicted by selection rules. And this is pretty complicated stuff to write these. You at least need a year of quantum mechanics. So you would take physical chemistry 1, physical chemistry 2, and then get into a quantum mechanics course to start understanding why these transitions can occur, what's allowed and what's not. But these are all things that have the commonality between these is they all have one valence electron. One valence electron. Okay, so lithium, sodium, potassium. They're all in the same period of the periodic table. So they're all in the 1A family. Now, this one is different. It's got two valence electrons. Right, so that's magnesium. So it's over 1 from sodium. And the numbers here are the numbers in angstroms. So divide by 10 and you've got the number in nanometers. And so we can go from, let's see if I can outline this as fine as I can. So we start down here with lithium in the 2s. It can do a jump to the 3p. It can do a jump to the 2p. The 2p can go to the 3s. The 2p can go to the 3d or the 4d. So those are the lines that we would expect to see for lithium. So there's 1, 2, 3, 4, 5, 5 lines we would expect to see. But if I look at sodium, sodium can go from the 3s to the 3p, go from the 3s to the 4p, or the 3p can go to the 3d, but this one that's, to me, the obvious missing is going from the 3s to the 4s. Okay, but that one's not allowed. It's called a forbidden transition. The selection rules say that quantum change can occur. That's well beyond what we need to understand to be able to predict when those are going to occur. The thing that I want us to take out of this is that this is where we get our uniquenesses in. Depending on what the nucleus is of the atom, even though the electron structure are very similar in these things. We're looking at valence electrons. These all have one valence electron. But even with that, different transitions can occur. This in atomic spectroscopy gives us the great ability to say this is with a great degree of certainty this element and only this element, because nothing else can match that exact. Okay, switching to looking at other things or just mentioning other things, then we're going to start talking about molecular spectra. Whenever we're talking about valence electrons, it's UV and Vis. Just the same way we talked about our exam question. If we go to X-rays, those are the core electrons that are being excited. Now switching gears to molecular, and I've already mentioned this. So molecular, E total, is equal to electronic plus vibrational plus rotational. And the energy is that electronic's the greatest, vibrational's the next greatest, rotational is the least. And there's about 100-fold difference with each step between them. And we represent that, and there's a lot of different ways that you can draw these energy level diagrams. This is one example of one. But what we have in this, trying to represent in this, is something going from a ground state, a lower level. So we represent a ground state. Ground state, and things being promoted to some higher excited state. So these are, anytime we're going up means that we're absorbing or capturing energy. That's going down in the direction of the arrows, it's losing energy off. Now, the way that we typically represent these is we represent the darker lines as electronics transitions.
It's 9:40, but
Okay, I'll finish this up and we're gonna call it quick. So these darker lines represent electronic transitions. So our electronic energy levels. And the lighter lines represent vibrational and rotational levels. So these are vibrational or rotational energy levels. Within each electronic, there are tons of vibrationals and rotationals. So when we think about the transitions that are occurring in the infrared, our spectras are just transitions that are occurring in the vibrational and rotational states. If it's a molecular species, it's a combination of. We have these electronic energy levels that are available, but there are tons of different vibrational and rotational within each electronic. So there are multiple transitions that can occur. And that's the reason the spectras are broad. And also, we're not going to start down here at a vibrational state. We're going to start somewhere in this, depending on where that particular molecule or atom is. This is your. I'm going to ask you this in a question somewhere. It's this nature that yields to the width of spectra of molecular speed. Atoms are sharp, discrete lines. Molecules are big, broad, honking continuums. Okay, and that's where we'll call our quiz today.